Welcome to our second MarRI-UK webinar, where we aim to give our members and participants an up-to-date snapshot of some current topics that are interesting to the sector. Today, we're covering the important and highly topical subject of nuclear propulsion for merchant ships. My name is John Hudson, and I will chair the webinar as Orla mentioned. Nuclear propulsion is not a new topic. The first nuclear-powered submarine entered service in 1955 and proved to be very successful, creating the first truly air-independent submarine. Since then, hundreds of nuclear-powered submarines and warships have been built, proving the technology to be very safe and very reliable. Early attempts at merchant ship propulsion, such as the Savannah and the Otto Hahn in the 1960s, were technically successful, but the ships proved to be unviable due to regulatory and commercial challenges. With the need for commercial reduction and energy security, there is now much renewed interest in nuclear propulsion for merchant ships, and we're fortunate to have three very knowledgeable speakers to bring us bang up to date. Rob Chaplin and Tobi Menzies from Core Power and Jez Sims from Lloyd's Register will take us through the technical, commercial and regulatory aspects of modern nuclear propulsion. As Orla says, we will have a short question and answer session at the end of the presentation, so feel free to start to fire those questions in when you wish. With that, I'll pass over to Rob to start us off. Rob.
Good afternoon, everyone, and welcome. Yeah, so I'm Rob Chaplin. I'm the Principal Marine Engineer at Core Power, and I'll just take you through some of the technical elements to commercializing nuclear power. There are three key pillars that we see in Core Power to success. One is a commercially insurable nuclear technology that can be operated in ports, and in particular around emergency planning zone limitations. We need to consider investment in that technology, and actually the development of it and that capital that we require, and aspects of the regulatory engagement as well. And then we need government backing. And so that proactive regulatory engagement and a political will for new nuclear maritime. So as we go into the commercially insurable technology, this is what I'll focus on. And then Tobi will take us into one of the other elements in a moment. The commercially insurable technology, we need to consider the size of that EPZ. Considering previous technologies, which we'll look at in a moment, the EPZ is quite large, and that basically brings an uninsurable element to shipping. We need to consider the safeguards around the technology as well, and that the fuel does not leave the reactor core, particularly ships move. So this is aspects around the movement of nuclear material, and we really need to avoid any need to refuel or handling spent fuel in commercial ports. And we need to consider the inherent and passively safe systems that are basically where physics protects us effectively. So in terms of conventional nuclear reactor technology, as you can see, operating pressures of boiling water reactors and pressurized water reactors are quite high. This has led to the large emergency planning zones that we see around those plants. And if you try and translate that into a ship, that large EPZ then follows that ship around. So any point that EPZ overlaps a landmass, then that emergency planning zone needs to be in effect. It's for that reason that we have been unable to ensure commercial shipping with conventional nuclear before now. So in terms of looking at the Gen 4 reactor options, we're focusing in Core Power particularly on the heat pipe reactor and the molten salt fast reactor, molten chloride fast reactor. So that's the HPR and the MCFR. We're in a number of projects at the moment that incorporate those technologies that meet our low pressure, so the correspondingly small emergency planning zone. From a safeguarding perspective, from an MCFR, you can conduct online refueling. So you have got quite a long fuel cycle, and you don't need to handle particularly that spent fuel. With an MCFR as well, the fuel is a liquid, so there is no meltdown risk. And for both the heat pipe reactor and the MCFR, you can see there that we've got walkaway safe, and then from an economic criteria perspective, high fuel utilization, they are quite compact and they operate at quite high temperatures in comparison to traditional reactors. And the benefit there is that you have higher thermal efficiencies. So as we see then, the operating pressures for the heat pipe reactor and the MCFR there, the ratio is about 150 to 1. So we are down as close to ambient as you can practically get. And that leads to a much smaller emergency planning zone, or that is the goal that we want to achieve, is demonstrating that emergency planning zone ideally will fit within the bounds of the ship. So from a commercially insurable perspective, you can then pull up alongside and your emergency planning zone is contained within your nuclear island. As I say, that is the goal, and that's where we need the regulatory engagement to make that case. So just very quickly on the programs that we are on with, so the molten chloride fast reactor, so we can see here, so we've partnered with TerraPower, Southern Company and Hyundai, and we're looking at what we call now the Delta program. So that's quite pre-conceptual at the moment. So looking at salt pumps, the fuel synthesis process and purification, material selection, component development, and then looking into the safeguards, security, non-proliferation piece. And we're currently working through TerraPower, working on something they call mock-up, which will use a chemically similar fuel for mock-up to prove thermal hydraulic models. And then we're working with a lab in the US on the molten chloride reactor experiment, so MarRI, and that will generate data that we need for baselining this technology. We move into the partnership we have with Westinghouse and their heat pipe microreactor. And so here we're looking at, it's about 5 megawatt electric, 50 megawatt thermal, with an unpressurized 5 to 10 year fuel cycle. And this comes in a modular form. So this is more mature than the MCFR work. So we're slightly more advanced in the development of the marinized version of this. In terms of requirements for marine integration, this is where the challenge lies. Obviously, reactors, they like to stay still, but ships by definition, they move. So we have some concerns that we have to work through, some challenges, particularly around accelerations and vibration, but also then roll and pitching moments. As I say, reactors like to stay still. And in particular for power, we need to consider the transients for the reactor as well, and how we try and separate the reactor elements from the propulsion element in terms of the motor, so that if you have an issue with one, with the propulsion side of things, it doesn't cascade up the chain into the reactor. And likewise, if you have a reactor transient, that doesn't work its way downstream into the propulsion element. And trying to achieve separation is another big challenge that we are looking to address as well. And then obviously from an accident scenario, capsize, sinking, collision and grounding, these things don't really exist for terrestrial plants, but these are accident conditions that we need to consider. And I'll hand over to Tobi.
Thanks, Rob. Yeah, that's great. So just to take over from what Rob has outlined, I guess my section of the short talk this afternoon is sort of in 3 parts. I first wanted to cover in pretty broad terms what Core Power is working on in addition to that, specific reactor technology development. And then I'm going to go into a little bit more detail on an unusual feature on the fuel inventory for one of the reactor types, and then finish up with a slightly closer look at some of the regulatory work that we're involved in before handing over to Jez, who's going to cover that in a bit more detail, most likely. So to start with, this is what Core Power is sort of aiming to do. We're not just co-funding and co-developing bits of technology that we're then looking to just sort of sell into the market. We're actually looking to build an entire maritime civil nuclear program around this, because really we see that there's little point focusing on just the technology development and hoping that someone else will figure out the other challenging parts to it, such as, as Rob's covered, the details of the interface between the nuclear island and the rest of the marine asset, also how these machines will be regulated and insured, how the assets will be structured and financed and operated, etc. So all of this sort of supporting ecosystem, if you like, needs to be built up around the technology, so that when the tech is ready, the rest of the systems are also in place and prepared for it. So just to reiterate, this program is based around, well, it's focusing on two separate strands, if you like, both self-propelled nuclear electric ships and also fixed floating power assets. And this is planned to be an industrial program for US and allied nations, whereby, working together with our program partners, we're designing and building these licensed, insurable, marine-ready new nuclear technology in key partnerships across the OECD. If I could have the next slide, please, Ola, that'd be great. Thanks. Now, I accept this is quite a complicated slide, and that's kind of the point, because with a few exceptions aside, as John mentioned, there hasn't been commercial maritime nuclear up to now, so we're kind of having to build the mountain as we climb it. Now, I'm not planning to go through every element here, but I hope this illustrates a little my last point, that we're working on several different fronts to develop the entire program. And you can see that one common thread, if you like, running from the top down through the green boxes in the center of this, and that thread is around jurisdictions to start with, then licensing and insurance, which is so crucial, as Rob mentioned. But the goal and the end result will be a fleet of owned and operated turnkey floating nuclear power solutions alongside customer investors. So the first time nuclear can actually be delivered almost as a service, a plug and play solution where the whole power plant is actually shipyard built and then delivered directly to coastal industry and to maritime customers. And delivering a turnkey solution in this way allows those customers to sort of confidently then choose reliable new nuclear to support more intermittent solar and wind, and to start replacing some of those heavily polluting fossil fuel assets, such as powering the large ships, as well as having FNPPs supporting heavy industry and communities on the coast. So we're working on all aspects of these new nuclear solutions, which solve those handful of key challenges that John and Rob outlined. And if we're successful, this could potentially unlock a very large market opportunity between now and 2060 across the OECD, both for nuclear commercial propulsion, nuclear commercial ships, and these FNPPs, or floating nuclear power plants, that I mentioned. Next slide, please. But for this middle section, I'd just like to zoom in on one particular aspect of the technology, which we feel is worth exploring a bit further. And it's around the fuel inventory for the MCFR, which is one of the reactor technologies that Rob highlighted that we're working on. For context, shipping has put around 1,000 billion tons of fossil fuels through its engines since the 1860s. That's resulted in over 3 trillion tons of exhaust gases. And all of that fuel that's ever been used, of course, had zero residual value. But what makes the molten salt reactor a real disruptor in this space, potentially, is the positive residual value of the fuel. And the way it could work is that the fast spectrum molten salt reactor, as we've heard, uses a liquid fuel, and that inventory is topped up at full power, rather than pausing the reactors and stopping the machines at refueling intervals to then remove the old fuel and to load fresh fuel. Therefore, the vessels don't need to stop outside their usual maintenance intervals. They don't emit any pollutants, as we've heard, and we can remove that small quantity of leftover waste from the core and store it safely inside the reactor island during operation without endangering anyone. So the reactor fuel inventory then is actually constantly full, and that's where the real game-changing effect sits, because what was loaded into the reactor on day one is still there, largely intact on the last day. If I get the next slide, please, Paula. Now, in this example, I'm using a $100 million asset based on a nuclear-powered, I think it's a Newcastle Max large bulk carrier, and a reactor at 150 million US dollars. So the host asset, the vessel, is here in the orange line, and it's depreciated as per the industry standard, a straight line method with 90% depreciation, leaving a small amount of residual value, say 10 million scrap value at the end of its trading life. And here, as you can see with the green line for the reactor, we've in fact depreciated that to itself to zero as well, along the same timeline as the rest of the ship. But that's taking a little bit of a conservative viewpoint, because the reactors themselves will be designed for slightly longer operating lives. They could go on to have a secondary purpose after vessel one, perhaps no longer on a ship, but perhaps on a barge making synthetic fuels or powering a port or something. But for this purpose, we've written it down completely. And then the next slide, please, Paula. But the fuel inventory that sits inside the reactor, however, is actually an asset that stays fairly constant, as we've seen, thanks to that inline topping up of the fuel. Therefore, this actually has the potential to behave differently. And at 2.5% inflation, an asset doubles in value over 30 years. So with a 30-year ship life, or on a floating production platform for synthetic bunker fuels, maybe powered by a fast spectrum molten salt reactor, the energy in the reactor system, all else being equal, could in fact double in value over time. And then next slide, please. So if you put all this together, you have the $100 million Newcastle Max, the $150 million reactor, and a $250 million fuel inventory, giving you a total capex, therefore, of around $500 million. Now, consuming bunker fuel, the same conventionally powered ship, say with a $60 million capex, burning fuel oil at $600 per ton, and that heavy fuel oil attracting carbon taxes at around $100 per ton, would cost roughly the same, around $500 million in combined capex and opex over the vessel life. Now, whereas consuming green synthetic fuels, e-ammonia, e-methanol, we estimate that cost to almost potentially quadruple to $2 billion over the asset life. Now, the potential economics of the same ship powered by an MSR has that residual value of the fuel going from $250 million on day one to $500 million at the end. And as per industry practice, some value needs to be set aside for a reactor decommissioning fund. OPEX and maintenance would be included, as is the specialized insurance cover. The liquid fuel at the end of the asset life could then be removed from the reactor, and with some reprocessing, it could then be reloaded and go into a next generation fast MSR for reuse over another 30 years in asset number 2, and so on and so on. So financing of the nuclear fuel part of this becomes quite a different proposition. We tend to advocate for leasing, and that's mainly because very few, if any, current commercial vessel operators would likely want or be able to become licensed duty holders or nuclear operators. And with the leasing of the fuel, the energy and the reactor system, we can then include that licensing piece, the liability insurance, and specialized reactor operations and the maintenance of the system all in the price. So here you can see on the fourth line the potential depreciation of the fuel for financing purposes, and the actual potential value of the fuel under 2.5% inflation. So it shows on the right-hand side that lease margin of around $300 million US, which is the spread between the actual and financeable value, inside which we can potentially construct a viable leasing model. So that's around 60% of the original capex. Now, the EU taxonomy allows for nuclear to be financed by green bonds. The UK has included nuclear in its taxonomy. The US government is encouraging investment in new nuclear, and also Japan, India, China, Brazil, and Canada, all encouraging private investment in their nuclear fuel cycle. So if the shipping industry is really looking for sort of sustainability across the board, both environmentally and economically, we believe this could be one of the answers in the future. And then next slide, please, Orla. And then my final couple of slides around some of this important regulatory work being undertaken. Rob mentioned it earlier, and I know Jez will go into more detail shortly, but I wanted to highlight a new industry association or an NGO in this space, which is called Nuclear Energy Maritime Organization, or NEMO for short. And it's been set up really to assist the top two regulators in this space, the IMO and the IAEA, as well as their domestic counterparts, in developing I guess we call it a fit for purpose and future-oriented framework of rules around floating nuclear. NEMO was launched in the early part of 2024, now has around 40 members. And as you can see from some of the logos there, both Core Power and Lloyd's Register have been involved very much from the outset. Next slide, please. I've just got 2 slides on NEMO, and then I'm going to pass the baton on to Jez. But we feel there are a few reasons that make NEMO a useful vehicle, if you like, as these regulators, the top regulators, look to either refresh some of their very old or out-of-date rules, or in some cases to create new ones. NEMO is concentrating solely on nuclear mobility. There are other NGOs that exist that deal with nuclear materials transport, but movement of nuclear materials is somewhat different to mobile nuclear technology in and of itself. So that's part of the background reason why NEMO has been set up. Its membership is drawn from around 8 different segments of both the maritime and nuclear industry. And as the right-hand box suggests, it's a forum really for that group to solve some of the major issues relating to those key challenges that we've sort of already looked at a little bit already this afternoon. So my final slide, please, Orla. And this just goes into a little bit more detail on those challenges and provides an overview of what each of those 3 working groups that have been set up are working on. In simple terms, Working Group 1 is very focused on the work around nuclear at the IMO, in particular the update of the nuclear code for merchant ships, which we feel could be tabled next summer at MSC 110. Working Group 2 basically considers kind of the mirror image of this in reverse, which is how the IAEA is considering maritime deployment of nuclear technology. And here you can see on the slide interfacing with Atlas. I know that's something Jez can speak to in a second. And finally, Working Group 3 is looking very much at the important concept of insurability of maritime nuclear and revising the principles of an international liability convention for nuclear ships. So if anyone is interested in their organizations becoming members of NEMO, please feel free to reach out to Jez and I for more details. But that's all Rob and I have on for our part, so thank you very much. I'll hand over.
Thanks, Toby. Good afternoon, everybody. Jez Sims. I work for Lloyd's Register. I'm the technical authority for nuclear, marine and offshore. And I've been with Lloyd's for about 1.5 years now. Next slide, please, Ola. Just like to start with a bit of a shameless plug for our nuclear fuel for thought. This is a production that LR have made, and it details some of the safety considerations, the drivers for adoption around nuclear, production of nuclear in the supply chain, and the technology readiness for nuclear as a fuel for shipping. This is a relatively high-level document for those that aren't intimately aware or experienced in the nuclear domain. So please go onto LR's website. There's a QR code there for ease of use, and it'll take you straight to it and maybe answer some of the questions that you might have. Thanks, Ola. So I'd like to start really with following on from what Toby was talking about, and John mentioned it earlier about this isn't the first time that we've looked at nuclear for maritime. And why are we looking at nuclear maritime now? I think it's pretty simple. The decarbonisation requirements, the global greenhouse emissions are driving companies and industry to look at zero emission fuels, whether that's ammonia, hydrogen, or nuclear, for how they can get around CO2 emissions in the future. And when you look at some of the emissions, the IMO regulations, this was revised in 2023. And it now has a 40% reduction in CO2 emissions by 2030 as a target, and then with achieving effective net zero by 2050. So you can see they're very ambitious targets have been set by the IMO for the maritime industry in achieving net zero. And there are other drivers as well, you know, the EU regulations, you know, the Fit for 55 and Fuel EU, which has got an 80% reduction by 2050 in CO2 emissions. And when you look at the carbon taxes that will be applied, as Toby said, I think they're about $100 per metric ton currently, and that's expected to go up significantly in the 2030s. So there's a real drive for the industry to move away from burning fossil fuels. So why do we want to go to nuclear? Well, you know, first and foremost, as we mentioned, nuclear is a zero emission fuel. There's no CO2, no sulfur, no NOx. So it's a clean fuel to use from an emissions perspective. And as Toby mentioned, the CapEx and OpEx relationship is very interesting in the way that we might be able to finance the operations of these ships. And Toby spoke about how what that could look like. But, you know, in addition to actually the finances behind it, one of the benefits it provides is stability for ship owners. If you've got a finance lease model, you know what that finance is going to be over a long projected period of time. So that takes away the uncertainty that there is currently around the fuel prices in diesel and gas. So there's benefit there. And as Toby mentioned, no bunkering requirements. You can have operational lives from 5 to 30 years, depending on the technology and the fuel density. And this can all be done with a number of different technologies, whether that's the microreactor, the molten salt reactor, high temperature gas reactor, pressurized water reactor, all with the advantages and disadvantages of each technology. Next slide, please, Orla. So we understand why we might want to use nuclear, but what else can nuclear do? Because as I mentioned earlier, we've looked at nuclear previously, and why did we look at nuclear previously when there wasn't this requirement for decarbonisation then? And simply put, the operational life, the removal of the bunkering requirement, the increased efficiencies and operational speeds of vessels that are nuclear propelled give an operational advantage to early adopters. And when you consider that 80% of global trade moves by sea, but 45% of high value goods move by air freight because the A to B time of maritime isn't quick enough to get these high value goods there. But if we could move maritime quicker, is there a percentage of the air freight trade that could be brought back into the maritime because it doesn't need to be there tomorrow, but it does need to be there quicker than today's A to B time? And if we can do that, and you look at the CO2 intensity around air freight being 10 to 50 times more than maritime, if we can bring just a relatively small percentage of that back into the marine industry, then you're going to significantly decarbonize the air freight industry, as well as increasing the amount of global trade moved at sea, which is already one of the lowest CO2 emitting industries worldwide, and only accounts for about 3% of global CO2 emissions. Next slide, please, Ola. Thank you. So coming on to the regulations that Toby mentioned, the nuclear regulations have been around in robust form since the 70s in a civil setting. We haven't had maritime nuclear regulations. The regulations that we do have are contained within SOLAS Chapter 8 for the Code for the Safety of Nuclear Merchant Ships, Resolution A491. This was never made mandatory. It's a voluntary code, and it talks about how to adopt nuclear in maritime, and it's very much a PWR and propulsion centric document. So as Toby mentioned, this needs to be revised and updated its modern standards to be technology agnostic and propulsion agnostic. And that's something that we're looking to get done at MSC 110, as Toby mentioned. But additionally, we need to have a international model of how to provide a required standard of nuclear shipping internationally. And that's very much something that the IEA and IMO need to work out together. This is something that we can foresee that SOLAS Chapter 8 491 will be, as and when it gets updated or proposed for update. And it's very much something that the IEA are looking at with Project Atlas. if we can jump onto the next slide, please, Orla. So Atlas. So what is Atlas? Atlas is atomic technology license applications for sea. In May this year, LR were fortunate to host the Director General Grossi at our headquarters in London, where we sat down with the Director General and explained our vision for what nuclear maritime would look like, how it can potentially transform the maritime industry, how it can help to decarbonize the maritime industry. And the Director General was very taken with this. So much so that in August this year, LR hosted the IEA's kickoff meeting for Atlas again in our London headquarters, where Atlas was proposed with an industry selected table of leaders within the nuclear industry, from insurance to manufacturers to class societies to ship owners, to discuss what Atlas could and could not be. And I think there was wide agreement that there are no significant blockers to nuclear maritime. Next slide, please, Orla. So Lloyds are currently working with the IEA with regards to Project Atlas. And Atlas, I think, will look to establish itself in a number of key areas around the requirement for regulations, for nuclear regulations in maritime, around the classification requirements. And as Tobi's slide suggested, classification is important because classification, as it currently does, is what gives the insurers the confidence that the asset is an insurable state. The insurance and liabilities in itself, the training requirements of nuclear maritime, and also the legal aspects around nuclear in the marine space, because as we know, currently sovereign nations deal with nuclear in civil nuclear very much within their own borders, and then now we're looking at potentially moving nuclear internationally across borders and how that works out legally. So Lloyd's Register really is looking to be a thought leader in this. We are currently working, as I said, with Atlas, with the IEA on the Atlas program. We're currently a founding member of the NEMO organization and are currently chairing their working group 1 in marine regulations. And we're also chairing the nuclear working group in IACS, which is the International Association of Classification Societies. We're also speaking to a number of national regulators to see how Lloyds are able to support them for the national regulators to understand what nuclear in the maritime space looks like, because national regulators such as the ONR, the NRC, are very good at regulating nuclear reactors in the civil space and understanding all the constraints and requirements that are involved around the licensing of civil nuclear reactors, but don't have very much experience in what that might look like in a maritime context. Whereas class societies obviously do. We've been doing this for centuries. We know what survivability and metocean data looks like for marine assets, and we can support the nuclear regulators in understanding the equivalencies between, say, seismic data and wave propagation and survivability at sea. And we're also talking with the nuclear regulators about the possibility of becoming a recognised organisation. Recognised organisations are something that class societies already do for the marine regulators, for statutory surveys and inspections, where class societies will be approved by the relevant flags to carry out these inspections on behalf of the flag and report back to the marine regulators. Clearly, the nuclear regulators, scaled as they are at the moment, wouldn't be in a position to have inspectors globally deployed to inspect these nuclear assets when in ports, where class societies such as Lloyd's Register already have that network in place and are able to provide that service for the regulators. So that's something else that we're looking at doing. And I think that covers everything off. And again, the QR code there for our nuclear fuel for thought, if you'd like to download that, and it may answer some questions that you have. John, back to you. Thank you.
Okay, well, thank you, Rob, Toby and Jez, for very clear and concise presentations. Please use the question and answer tab to fire in any questions. And while I wait to hopefully get some questions from you, I've just got a couple. So the first one is the naval sector. One of its failings has been in decommissioning. I think many aspects of the way the naval sector has worked has been very effective, and performance of nuclear plants at sea has been, outstanding, really. But I can remember when we were designing the Astute class submarines, there was actually no requirement to consider nuclear decommissioning, which, looking back, seems an extraordinary situation. So I was just wondering, whether at the outset of these things, how much decommissioning was considered, both in the context of fuel, but also in terms of redundant plant, how much that factored into that thinking. I don't know whether that's one for Rob or Toby. I'll let you choose.
So I'm scrambling to find the unmute button here. Yeah, we can certainly speak to that. I mean, I think the quick answer, John, is that it's absolutely conceived from the outset and to be an entirely circular, a circular sort of piece, whereby the asset may not be, the future nuclear asset may not be entirely built in one place. It may be that the non-nuclear part is built in a part of the consortium's favoured shipyard somewhere else in the world, and then it comes to a nuclear shipyard for integration of the energy island, if you like, into that system, and that's where the fueling will take place. After the asset, well, during the life of that asset and the maintenance cycle of that asset, it would periodically return to that nuclear shipyard for that work to be done. And also when the asset is ready for decommissioning, the same thing will happen. It will go back to that facility where the nuclear island is removed. Then the vessel, the balance of the vessel is a non-nuclear asset. After that, it can go off for recycling in the sort of traditional way, if you like, as long as it meets the Hong Kong Convention. But then that nuclear part will be recycled in a way that the industry already knows, the secular industry, I should say, already knows very well how to handle. It will depend a little bit on the individual reactor types around exactly how that fuel reprocessing takes place. But I think, as I alluded to, with the liquid fuel, that really is a game changer in terms of what's possible and how it's chemically undamaged at the end of its life, provided that reprocessing can be done. It could actually then go on to have a life in vessel 2, which is unprecedented as it stands now. I think maybe Rob has something to add on there, but that's how we see it.
No, that's exactly it, Toby. And the molten chloride reactor experiment, the MarRI activity that's going on at the moment, that includes an element of disposal. So it takes the fuel cycle from its initial synthesis all the way through to disposal. Yeah.
Very good. Thank you. So we've got some questions coming through. So I've got one for Jez, which is, how is LR going to train surveyors and recruit them for nuclear shipping?
Yeah, cheers, John. That's a very good question. I think first and foremost, we need to understand what our remit will be in this space. And that's very much, as I said, something that we're talking to the nuclear regulators about, because we first and foremost need to be able to demonstrate to the regulators that we're competent and credible to be able to carry out these inspections and surveys on their behalf. I think our intention is to be able to do as much as we can possibly do. And when we understand what that looks like, obviously we'll have to construct a qualification in the same way that we are going to have to for the other alternate fuels, for ammonia, for hydrogen, and the same way that we have done for traditional shipping. There is, depending on how much we get to do with the plant, nuclear plants aren't incredibly complicated bits of kit outside of the core. You're talking about piping, pressure vessels. There's obviously a radiological element that needs to be understood, and I suspect that will be a prominent part of the training, will be understanding the radiological element and how to deal with that. But if we have to bring in specialists or provide specialist training for certain elements of the surveys, then absolutely that's something we'll look to do. Recruitment, yeah, good question. We're going to be battling with everybody for the nuclear SQEP, as industry, both defence, civil, maritime, all scramble for nuclear SQEP.
Very good, thank you. So Patrick Carney's asked a couple of questions, and the first one is, what do you see as the sort of core areas requiring innovation and innovation support you know, are the technologies and areas that might need government funding or you know, academic support, or you know, what are the areas that are going to need substantial input from other parties? I don't know, Rob, do you want to have a go?
Yeah, I can sort of chip in. So from a technical perspective, I think where we're sort of heading with this at the moment, with the sort of, we're still going through the motions of updating standards and things that are they're not technology agnostic. So actually, where we sort of need to innovate is actually in the process space, I would suggest, in terms of understanding, you know, that risk-informed, performance-based evidence that you generate as part of your application submission to the regulator. It's trying to align that, I think, with what class want to achieve as well, so that you go through the same processes. You just build the body of evidence in a slightly different way for consumption by the regulator versus consumption by a class. And at the moment, that's sort of the big thing that's up on my radar at the moment, is that I really don't want to have to go through two separate processes for marine side and for regulation side. And I'm really keen to explore sort of like that risk-informed, performance-based approach and bring an element of innovation over the top of it, so that we can approach it in a singular way and then construct the body of evidence for submission to each organisation.
It's always interesting to learn the lessons from other sort of areas, and I can't help harking back to naval nuclear propulsion. And I think if we were to look back on the programme, one of the most challenging areas was materials. You know, the juxtaposition of different materials and the use of basically electrolytes in the system as well created all sorts of phenomena that we didn't really anticipate at the outset of the programme. So how confident do you think you are, particularly in something like a molten salt reactor, that we've really got the materials technology to make sure that we've got the sort of lifetime that we anticipate for these plants?
Oh, that's a great question. And yeah, so from a materials selection perspective, so we're relying quite heavily on MarRI, and also another earlier mock-up that being put together that uses a chemically the same molten salt. And yeah, it's understanding then, in terms of the accident conditions, you know, if you introduce water from your steam range in, you know, through your steam generator, and you get that into your molten chloride loop, what the consequences from a from a chemistry perspective, and then are the materials suitable in that accident condition? And yeah, it's a great question. It's something that we're really working hard on at the moment in that material selection, and also qualification as well. You know, you can find that material and go, this is absolutely brilliant, but if it's not recognized in the standard, then you sort of have to go through that whole qualification process to get it added to that standard.
Yeah. Just to add on to that, I think that Rob's obviously right. There's an enormous amount of the vast majority of the work that's being undertaken around the molten chloride reactor experiment is around corrosion mitigation and control. Huge, tens of thousands of hours have gone into considering this, and I think I wouldn't want to pretend that we've absolutely solved it, but the progress is definitely there, and there's incremental steps all the way to having a solution. I think when you compare some of the early sort of pipe results compared to how they look now, it's obviously very different, and there is vast progress being made. A lot of it relates to the purity of the salt mixture, and not allowing any impurities in there. But obviously, there's a trade-off then between you know, it takes quite an effort to get to 99.9% purity of your salt before you start introducing fissile. So it's getting that balance right. But that's an enormous amount of work being undertaken in Seattle and in Idaho about that.
Very interesting, thank you. So the second part of Patrick's question was really one about sort of public perception, and you know, one of the things that dogged the sort of commercial nuclear program previously was people's willingness to accept the ships into harbour and things like that. So I think Patrick's question is, you know, how do you see NEMO and other organisations building public confidence to tolerate this type of technology? I don't know, Jez, do you want to have a go at that one?
Sorry, what was that one, John? So
it's just about how do you build public perception to be confident in nuclear tech? Nuclear, unfortunately, has a sort of negative connotation to it, and naturally there'll be a a nervousness and a reaction to it. So how do we build the public's confidence in nuclear technology?
So no, you're absolutely right. The nuclear comes with a lot of baggage from historical events and the perception that has been, or the narrative that has been fed to the public over the past few decades. And quite simply, the easiest way to deal with this is to just rely on fact-based conversations and deal in facts and facts alone. Obviously, there's an element of education and interaction. There needs to be, transparency with what we're doing. We work with the regulators, with the the port authorities and the shipbuilders, especially in areas where we're intending to operate these assets, because you need to have public confidence in what you're doing, because public confidence, if you don't get it right, can have a significant impact on both political and regulatory pathways. So it's important that the interactions are there, that the public engagement is there, and that people are given the opportunity to voice concerns, to ask the questions that they feel they need to ask, and that we've got fact-based answers, not conjecture or opinion, but just fact-based answers to support the claims and positions that are being made, because that's the only way that we can combat this historical narrative, is with facts.
Yeah, very good. Thank you. Alan Williams has got a question, and it's about the sort of longevity of these projects. If we're talking 20 to 30 years, and then there's a terminal activity, the decommissioning phase, that means that enterprise or something has to be in place at the end of the project. And so the question is, how do we ensure that continuity and the funding will be available such that we can do the decommissioning as anticipated? Is there a model for how that will be financed and supported?
There isn't a completed model yet, but it's something that we're working on all the time. I mean, I think as I mentioned in my slides there is already, with terrestrial nuclear, a decommissioning fund that's built into operations of terrestrial, mainly PWR plants. That will of course have to be carried over into the maritime space. When we talk about nuclear shipyards, I think it's not necessarily going to be a small add-on to an existing already built shipyard. I think it will be probably a US-based gigafactory type environment rather than a traditional shipyard. So there will need to be all of that infrastructure built up. But it's the nuclear decommissioning fund that will be paid into throughout the life of the asset that's covered. Well, the asset, of course, will be controlled by a consortium that involves the nuclear duty holder, and the reactor developer, and obviously some investment parties as well. So that will be where the decommissioning fund pays from.
Thank you. So please, if there's any more questions, do fire them in. Just one more from me, which is, where do you think the commercial balance point is at the moment? You've sort of suggested that the ship could be, with its fuel and reactor, potentially 4 times the cost, the initial investment cost of a normally propelled vessel. So, and obviously fuel cost through life would be much less. So I just wondered if there's a sense yet of where that commercial balance point is, and whether we're going to need something like carbon tax or something of that nature to actually drive incentive into making nuclear financially viable.
Yeah, I think shipping always kind of goes for the lowest common denominator. I think if heavy fuel oil plus a low or very weak carbon tax is what happens, and that ends up being the cheapest solution, that's where shipping will predominantly go. It's where the current fork in the road is with the high cost of green electrofuels, where I think we're going to see the biggest delta, and carve a natural space there for nuclear propulsion. Because as we're finding out now, increasingly the cost of making those green fuels is exorbitant. So that's where I think we'll see some early kind of commercial possibilities, not necessarily purely competing with heavy fuel oil plus zero carbon tax. I think it will be quite close there, broadly speaking, as to whether that's workable.
Do we have a sense of how big that challenge is? Is it 10%? Is it 20%? Is it 100%? Is it how close is nuclear propulsion per kilowatt hour to conventional propulsion? Do we know yet?
No, I don't think we have it. We have a definitive answer on that. I think it's still a little bit too early to say.
Jess, were you going to come in?
Yeah. No, and I think Toby's right. I think you know, to postulate around numbers now would be somewhat disingenuous, given that we don't know. You know, I think it's fair to assume that the early adopters are going to be, you know, relatively expensive compared to the projections. What we do know is that for nuclear to become economically viable, and I've seen projections that would suggest by 2050 it could be as cheap, if not slightly cheaper, than heavy fuel oil is today. You know, where are we getting those numbers from? You know, obviously there's sources behind it, but there's so much that has to happen between now and then for that to become a reality. If we don't find a way of, first and foremost, having a supply chain that supports the adoption of nuclear maritime on a scale that it will need to be for the mass production of these modular reactors for maritime, that come with an element of or licensing pathway where they're pre-licensed through manufacture, assurances provided, such that the operator, the licensee, needs to come in at the back end, and then, you know, almost in you know, what we'd like to see is something very similar to how we you know, the purchase of gas turbines is today. You know, they're mass produced, they're assured, pre-licensed. You come in, you know, you have the operational envelope that you want to use it within, you fulfill the licensing requirements, and you go away and use them that way. If we don't get the supply chain, you know, the fuel manufacture, the manufacture of the reactors themselves, the build of the ship in licensed yards, the regulating, you know, because regulating is expensive today in civil. You know, if we don't get all these elements to work concurrently, then nuclear is going to be expensive. So it's important that the whole package is taken, and that we manage to get that where it needs to be, when it needs to be there, to enable, you know, large scale adoption of nuclear maritime, because only then will it become well, economically viable and ideally, you know, a cheaper option and operationally beneficial option.
Very good, thank you. So Alan Williams has just asked a sort of follow-up question, which is, clearly ships are produced mainly in sort of China and Korea and the Far East at the moment. And so he's sort of questioning what would happen at the end of life of these nuclear propelled vessels. I think you've talked about a nuclear island. So I presume the nuclear island could be built either in those countries or possibly in another country. And there's a question about who would own the liability for the fuel. Would that be a national thing, or would that be the producer who'd be liable for the fuel? So, you know, do we have a thought about, you know, who's going to contain the liability at end of life from a national point of view?
Yeah, so I mean, Jez can maybe speak to some of those safeguarding elements around the fuel, but just going back to this shipyard piece, I think I'm really talking from our perspective as a co-developer of two particular technology types. Those two technologies are being developed in the United States. So at least in the first instance, we expect that facility which builds the reactors, integrates them into the machines, and fuels them, will be in the United States, and they will have to go back there at the end. So it'll be done under NRC, national regulating conditions. We're not anticipating that nuclear ships will end up on beaches in India or Bangladesh, or even going back to the place where those shipbuilding countries that are suggested. I think that's a key point to make from the outset.
Yeah, very good.
It might be in the future that those reactor vendors from the United States achieve export control guarantees to be able to build them in license in third-party countries, in allied countries. But that is some way away yet. I would say it's going to be probably American-led for at least for our reactor types.
Very good. Well, look, thank you everyone for firstly to Toby, Rob, and Jez for very clear and interesting presentations. Thanks all to participants for the questions that you've answered, that you've asked. If there are any burning questions, then or if there are any comments about the way we've run the webinar, then please send them through to the MarRI-UK administrator. That's all is sort of addressed. So if there's any feedback for us, please do give it. And if there are any other questions that come to mind, we'll attempt to get those answered. In the meantime, thank you very much for your joining the webinar today. And I'd just like finally to thank Orla for setting this up and making it run as smoothly as it has. So thank you to everyone, and we'll call it a day there. Thank you.
Okay.